Alright, so hello everyone. This is Akash and welcome back to my channel. And yeah, it's been a long time since I uploaded. That is primarily due to my intern. Like I got pretty busy in the work, so like I lost track of my YouTube videos and all those things that I had, like upcoming things that I had for planned for this channel. So yeah, I'm sorry for that, but I'm trying my best to manage my time. Like I don't even get the time to solve problems, and uh, and I hate that. But yeah, it's a new thing, and I'm enjoying that. So yeah, that's kind of an update. And yeah, anyways, today I just thought of teaching merge sort trees. So last in the last lecture I taught segment trees, and I actually think that I did okay job there. So to understand merge sort trees, I would highly recommend you to first watch the segment trees, as merge sort trees are just a variant of segment trees itself. So it might help knowing the segment trees first. And The merge sort trees are actually not very different from segment trees. There's just a little bit of differences here and there. So yeah, we're gonna see everything. And yeah, so let's begin. We're gonna see if we can complete this in 20 minutes, because the segment tree one was like a little too long. So yeah, let's go. Okay, so what exactly is a merge sort tree? So like we learned in the segment tree, each node of the segment tree, stored some information about a segment, right? So each node of a segment tree stored some information. So let's say this node stored the information for node one, for indices 1 to 2, right? Something like this. But the difference between a segment tree and a merge sort tree is that in this node, that is this one, we not only store information, but we also store the sorted order of values, right? So let's say this was my original array. So array was 4 2 10 3. This was my array of size 4. Okay, so now let's say the last node only stored a single element. So this stored the first element, this stored the second element, similarly this is stored the third and fourth element respectively, right? So this node stored information from first element to second element. So that was what segment tree was doing. But merge sort trees, on top of that, stores the elements in the sorted order as well. So in this particular node, we store the elements in a sorted order, right? And similarly, just a minute, similarly in this one also we store the nodes in the sorted order. And then when we merge, we just do this via two pointer technique, that we have one pointer over here and one pointer over here, and then we create another sorted list by using the left and right children. So like I have this pointer over here, this pointer over here, I check which one is lesser. So 2 is lesser than 3, so 2 will come first, and then this will move this one ahead. Also we took 2, so we'll move this one ahead. Now we'll compare 4 and 3. 3 is lesser than 4, so we'll add a 3 over here. Cool. So we chose this 3, so we'll increment this further, and then we'll increment this further. Now we'll check which is lesser, 4 or 10. So 4 is lesser, so we'll add a 4 over here. This is done. So now we'll go over here, and then we'll add a 10. I hope you get this. Like this is just this is the primary difference between a merge sort tree and a segment tree. This merge sort tree is, on top of storing information, also stores the elements of the array of that range in a sorted order. That is the primary difference. Now why exactly that comes into use, we'll see a problem, and then we can discuss how exactly a merge sort tree comes into hand. So yeah, I've written a problem over here. You're given an array ARR of size n and q queries. Each query consists of L, R, and K. So each query consists of 3 parameters, L, R, and K. L, R are the segment ranges. So a segment starts from L and goes all the way up to R. We need to find all the elements which are strictly smaller than K. So like if this was my array above 1, just a minute. If this was my array, and then my, say the range was 2 to 4. So like one based indexing would take me from this range would be what we were talking about, 2 to 4, and then K is 1. So not 1, let's consider 5. So if K is 5, we'll return 2. because two elements are lesser than 5, which are 2 and 3, right? So this is what exactly we need to do. In the range L to R, we need to find how many elements are strictly lesser than k. The brute force solution is very straightforward only, right? Like we can run a loop from L to R, just check if the elements are lesser than or lesser than k. If they are, then just increment the count and return the count in the end. But the brute force solution would have the complexity of n into q, which is not what we want, because n is up to 10 to the power 5 and q is up to 10 to the power 5 as well. So this might result into TLE, not might, this will result into TLE. So we need to optimize further. Okay. So now how exactly a merge sort tree can come into hands, we'll see that. So to see this, let's consider this case. Let's say I have this left children where I have these values like 2, 4, 5, 12, cool. So this is my left children. Just consider this case for now. Then I have my right children over here as well. So like right children consist of 6, 8 and 9 and let's say 20. Okay. So now I'm saying my k is what, 10, let's say, cool. So k is 10. I need to find in this particular range, So this, let's say this stores the information from 1 to 4, and this stores the information from 5 to 8. So 5 to 8. Now I need to find the number of elements in the range 1 to 8. So this complete thing, and k is 10, so strictly smaller than 10. All the elements, the number of elements strictly smaller than 10. Cool. So now I have these two children. Now to do this efficiently, what I can do is find the lower bound of this element 10. So 10's lower bound over here is 12, right? Lower bound means what? Lower bound means the element is either exactly equals to k or greater than that. Like it's a technique in binary search, right? Lower bound and upper bound. So upper bound is the element has to be greater than the current element. So upper bound of 10 is 12. Upper bound of 10 is 20 in this one. In this one is 12, right? But the lower bound says that the element could be also be equal to the k, or also equal to whatever we are comparing it with, right? In upper bound it has to be greater, but in lower bound it can be equal. That is the primary difference between lower bound and upper bound. So I need to find the elements which are strictly smaller than k. So essentially what I can do is just find the lower bound of k. So lower bound of k gives me, let's say this was 0 based indexing or 1 based indexing, whatever you want to take. So 1, 2, 3, 4, 5, 6, 7, 8. So I did a lower bound of 10 in the left children, which resulted into 4th index. So 4th index, this says I am on 4th index, and 4th index is the one which is strictly greater than k. So if I need the elements which are strictly smaller than k, right? So if we need is strictly smaller than k, that would be the answer, the lower bound minus 1, right? So 4 minus 1 would be 3. So I'll have 3 elements which are strictly smaller than 10, right? So let's say this was 10, not 20, it was 10 in this case. I did a lower bound in this one. So the lower bound is equals to this, the 8th element, or the whatever you want to call it, right? Let's say this was as they are like separate arrays, so the real indices would not be 5, 6, 7, 8, but 0, 1, 2, 3, taking 0 based indexing. Here also 0, 1, 2, 3, and in 0 based indexing you don't have to do I minus 1, because lower bound itself is the number of elements on the left. So like if my lower bound's index is 3, that means I have 3 elements which are strictly smaller than k. So similarly over here k, the lower bound of k is the 3rd element, 10 is equals to 10. So now I need to calculate how many elements are strictly smaller. So all the elements to the left of this thing are strictly smaller. That are 3 elements to the left. So this is my answer. So now this will return a 3, and then this will return a 3, and then what our answer would be, 3 plus 3 would be 6. So 6 would be our answer. So this is the same logic that we did in segment trees. Like the differences, the segment trees did not had sorted list of the array elements. The merge sort trees stored the sorted order of elements. And then we can do this for all the nodes and combine the result, add the result, and get the answer respectively. The thing is, the time complexity for querying would be log square n. Why log square n? Because I'm doing a binary search, which is lower bound is essentially binary search. Both lower and upper bound are binary search. So lower bound is essentially log base 2 of n, and since querying in a segment tree was log n, so log n into log n for binary search, so that is log base 2 of log base 2 square of n, right? So log square of n, that is. The update query is essentially order of n. We're not talking about update here, but the update query will be order of n. Why? Because we are essentially rebuilding the complete array, right? So if this element changes, let's say this element changes, so I'll need to update this in the last one where the 9 was present, and then build the complete array again. So like this thing again, then its parent again, its parent again, its parent again. So I need to combine the arrays again, and in order to combine the arrays again, I need to iterate on the arrays again, which will be order of n, right? And I may be wrong, maybe it's order of n log n, because there are log n levels in a segment tree, right? So there are log n levels in a segment tree, and then in the worst case we might end up combining n elements, so that is order of n log n, right? So the update query is not n but n log n, right? Okay, but we're not talking about update, we're only talking about queries over here. So yeah, the query is log base 2 of square of n. So that is how we'll exactly solve this problem. We can see this through an example. Let's say I had an array 24, 12, 14, 10, 6, 5, 1. This was my array. So how we'll build a merge sort tree is, this is my last level of nodes. Now the parent is, we'll combine this in a sorted way. So 4 and 20, my pointer is here, my pointer is here. Which one is smaller, 4 or 20? 4. So append 4 first and then take a 20. Cool? So this is formed. Similarly 12 and 14 are formed, 6 and 10 are formed, 1 and 5 are formed. And now when I form this, I have one pointer over here, one pointer over here. Compare 4 and 12, which one is smaller? 4. So add a 4 over here, move to the next element, which is 20. Which one is smaller, 20 or 12? 12. So add a 12 and then move on to the next one, which is smaller, 14 or 20? 14. So add a 14 and go to the next one. We don't have anything, so we'll just insert all the remaining elements of the first children, right? This one. So I'll add 20 over here, and I'm done with my iteration. I formed this this node in the merge sort tree, right? So this is essentially how we'll construct the merge sort tree. So when I'm querying this, again we'll have the three possibilities: the complete overlap, so the complete overlap, the partial overlap, so the partial overlap, and the what we'll call this, like exclusive, क्या बोल सकते हैं इसको, like this is like mutually exclusive or not, like outside overlap, let's call this outside overlap. So like it has nothing in common. So like complete overlap is ki I need to find from L to R, and in the node where I am currently, which is L dash R dash, that completely resides again inside L to R. So we'll need the complete answer, so return the answer from here. The partial overlap is something like this. So in the partial overlap I cannot take the complete answer because that will result into some extra data that we don't need. So we'll go to its two children. If it's like not a it likes completely lies outside, then this will have nothing that we want for this answer. So we'll return 0, or like an identity element which doesn't change my answer, right? So this is exactly this remains exactly same as segment tree. And I told you how we'll do the nodes logic. We'll just binary search on each node, and then we'll have our answer. So that is exactly how we'll do it. So the querying time is log base 2 square n. That is essentially like we're doing q queries, and then each query takes log square n. So this is q into log square n complexity, and then this will get accepted into whatever just you are trying to write code in, right? So this is what a merge sort tree looks like. It's the same as segment tree again, and let's talk about this complexity. So the build is order of n. Again, I think this is wrong. This would be at the order of n log n, because there are log n levels, and we need, like in the worst case, to form the complete array which is size n. So like we might end up traversing the whole array, right? So like what I'm talking about is in the first node, the root node, we might end up iterating on all the elements, right? So there are n elements, so we'll need to iterate on all the n elements. So this is like n, and there are log n levels, right? So this log n into log n would be like, I think so, I might be wrong, you can google the complexity. The querying would be log square n over here at least, and I think like different problems have different complexities. So like the problem, I think the count inversion one would be log base 2 of n only. I don't actually remember, I might need to think about it. But yeah, different problems have different complexities. The update is again n log n. I may be wrong, maybe, but I think it is n log n. Space complexity is again n log n, because there are log n levels, right? There are log n levels in segment tree, or you can call it a merge sort tree, and the array size of each node could be the n in worst case, so n over here, n by 2 over here, n by 2 over here, right? N over here, n by 4 over here. So this is nothing like, this is in the worst case n only, right? So I have log n levels, and the array size of each level is n, so n log n is my space complexity as well. I hope you get this. And now you can see the implementation. It's fairly straightforward, just like the segment tree. So the vector of, I created a 2D tree to store the array elements, sorted array elements, right, in a node. So this is like, we resize this to 4n, right? Then we call the build function from 0 to n minus 1. Now when l is equals to r, that is the last leaf node, then we'll insert the only node into our array, and then we'll return from there. We'll calculate a mid, call the function for left, call the function for right, then we'll merge both of them over here, right? This is like we are resizing the current node. So like, let's say I'm over here, and the left children had the size of 1, right children had the size of 1. So the size of this thing would be 1 plus 1, which is 2. So this is what I'm doing. Tree node of resize is resizing it by the left children, which is 2 into node plus 1, the right children, which is 2 into node plus 2. So adding both of their sizes and resizing the current parent child, right? So the parent node. So that is what exactly I'm doing. Then I'm merging the left children and the right children, right? So I'll have written the merge logic. Okay, though the merge logic is not over here. Let me check if I have in my template. Merge sort tree. So the merge. Okay, this is okay, I think this is a standard C++ thing. Like I never in my life used a merge sort tree like using a template. I just wrote it today itself, so I don't know. But I guess this is a C++ STL. Like I'm taking my left children's array, the right children's array, and then I'm combining this in the tree node.begin. So this is my iterator. So I'm combining these two arrays in my in this iterator. So this is my starting iterator. So I think this is a C++ STL function. Then query, query we have three things, like if this is a mutually exclusive interval or node, then return a 0. If this lies completely inside, this is this logic. If it lies completely inside, we find the lower bound, and distance is again an STL, C++ STL, which gives the like, if this distance was like I was querying like the elements in the array were 5, 7, 10, 12, and I was querying k equals to 12. So this would be my iterator, where the index would be 3. So this is essentially converts this particular iterator. So lower bound of this k in this tree node dot begin to end. This gives the distance, actually gives the distance. So tree node dot begin and this iterator, I pass this iterator. So this returns 3 over here. So 3 elements are lesser than 12. So this returns 3. This is exactly that. And then I do a mid, and then I call this for left and for the right one, and then I add my result, and then I get the final answer and return that. So this is exactly like the segment tree. And some more famous problems are, you can try solving count inversions. It is a very famous problems, asked in a lot of interviews. This problem is also very famous. Like we need to find we need to calculate the number of occurrences of a specific number x in a range. So let's say these were my elements 1 4 10 11 14 16 16, and I need to calculate the occurrence of 16 in this particular range. So how exactly we'll do that with merge sort tree? That will come handy. This merge sort tree will come handy in problems like these. You can google the problems and try solving some more, so you'll get a better idea of how, on how exactly this works. And yeah, this is pretty much it for today. How much time it has been? It has been 20 minutes exactly. So yeah, we were on time. And for the people who did not understand, I would highly recommend first to watch the segment tree lecture, and yeah, if not from me, watch it from anywhere. Like you should know segment trees, like the basic implementation of segment trees, in order to understand the merge sort trees very well. Like you'll get the intuition of how the merge sort trees work very well, right? So yeah, that is it for today, and I hope you got it. If you actually got and learned something new, then please let me know in the comments. I know I'm uploading after a long time, so I'm sorry for that. And I'm planning a lot of lectures like on string hashing, game theory, and other advanced CP topics. I myself am not that confident, but through this channel, it's like I revise my own concepts, and like these concepts also become crystal clear in my head while I explain also. So that is exactly why I do it, and I hope you got it. And yeah, that is it for today. Thank you so much for watching, and I'll see you guys in the next one. Till then, bye bye and Radhe Radhe.